thinking more about energy and oscillating systems. So we're focusing on the mechanical energy, just kinetic plus potential energy. And remember from last time, when there's no friction, that, that mechanical energy stays constant. Here I've written out the two kinds of energy, kinetic and potential. And if the mechanical energy stays constant, then the value you calculate at any one point in time for any particular speed and any particular displacement away from equilibrium is going to be the same value that you calculate any other time. For example, if you calculate using the numbers you measure when the oscillating object is right at equilibrium, well, remember from last time, when the object is at equilibrium, it's got its maximum speed. And when it's at equilibrium, obviously the displacement away from equilibrium is zero, so no potential energy. So that number is equal to the total mechanical energy. And similarly, if you measure things when the mass is at its maximum displacement away from equilibrium, well, being at maximum displacement away from equilibrium means it's not going any farther. In other words, it has come to a stop. So it's stopped. Speed is zero, so there's no kinetic energy. All you have is the elastic potential energy, and the displacement away from equilibrium is at its maximum. The maximum distance away from equilibrium we call amplitude. So I've written delta x as A for amplitude there. So, but that's one way of calculating mechanical energy. And when you see that the total mechanical energy of a system is just this number, one result is that there's a relationship, a proportional relationship between mechanical energy and square of the amplitude. Which means, for instance, if there is friction, what happens when there's friction? Thermal energy increases. The work done by friction has the result of taking away other kinds of energy, mechanical energy, and transforming it into thermal energy. So when there is friction, mechanical energy decreases, and that lost mechanical energy shows up as thermal energy. Well, if the mechanical energy decreases, then the amplitude decreases. And if you wait long enough and allow friction to do work for long enough, it can take away all of the mechanical energy and turn it all into thermal energy. And of course, at that point, then the oscillation has come to a stop. No mechanical energy means, among other things, no kinetic energy, so no speed. Graphically, here's what that sort of thing looks like. Imagine a graph of location versus time for the oscillating object. We'll say that the equilibrium position is right here at x equals 0, and we start by let's say it's a mass connected to a spring again. We start by pulling the mass and thereby stretching the spring, pulling it away from equilibrium by some distance. And then, of course, when you let go, it oscillates back and forth about equilibrium at some particular frequency and period. But if there's friction, mechanical energy is being taken away, and you see that mechanical energy is being lost because you'll see the amplitude of oscillation decrease. Every half cycle, the maximum distance away from equilibrium is smaller than it was a half cycle earlier. Something like that. Now, if you draw a curve that connects all of the points of maximum displacement away from equilibrium, you can show that that curve is actually an exponential curve. That is, let's is amplitude changes as time goes by because mechanical energy is being taken away, so that decreases the amplitude. Amplitude is a function of time, and in particular, it looks like this, where A is just the amplitude right at the start. That is, initially, I stretched the spring by a distance of A meters. I moved the mass A meters away from its equilibrium position, and then E to the minus time elapsed over tau. Remember from the reading what tau means. Tau is a so-called time constant. It gives you some idea, some numerical quantitative sense of how strong or how weak the friction is. If you have a strong friction force, then of course it'll do a lot of work every cycle, and the amplitude will decay very quickly because that friction, the work done by friction, is converting mechanical energy into thermal energy very quickly. And that corresponds to a very small value of tau. And then in the opposite situation, if the friction force is weak, then it takes a long time for friction to do enough work to make to transform all the mechanical energy into thermal energy. So it takes a very long time for the amplitude to decay away. So strong friction force corresponds to a small value of tau. Weak friction force corresponds to a large value of tau. Well, how do we know that? Why does that make sense? Well, let's think about what's happened here to the amplitude after we've been watching the oscillator for tau seconds. Tau is some length of time. So amplitude at time equals tau seconds after the start is just original amplitude, e to the minus time equals tau over tau. So you have tau over tau, so that's e to the minus 1. And any number to the minus 1 is the same as the inverse of that number. That number, that irrational number e, is a number that you can get a good approximation for it from your calculator, but what it comes out to is about 1 over e comes out to about 0.37. So in other words, after tau seconds, the amplitude is about 37% of what it was at the very start. It's the amplitude has decayed away by almost 2/3, or 63% to be specific, almost 2/3. Now we can look at some more complicated situations involving exponential decay here, but to do that, we need to recall an old trick from algebra, logarithms. Logarithms are all some kind of an exponent, and there are different kinds of logarithms that act as different kinds of exponents. The exponential function e is related to a particular kind of logarithm called the natural logarithm, abbreviated ln. That's the label for the button on the calculator, and the natural log function, we'll just write like that. As I just said, every logarithm is an exponent of some kind. So natural log is an exponent of some kind. So y is just the name for a particular kind of exponent. What kind of exponent? Well, this exponent is the power to which you raise e in order to get whatever is in that slot in the natural log function. So that's helpful because you think about this for a minute and you can see that the natural log sort of undoes whatever the exponential function did. Let's think about that. Imagine that we take the natural log of e to the y. Well, this is an exponent. Every log is an exponent. What kind of an exponent? This thing here that we're trying to figure out, this thing here is the exponent to which you raise e, the power to which you raise e in order to get whatever is in that slot. So, to what power must you raise e in order to get e to the y? Obviously, y. So what the natural log does, it has the effect of pulling this exponent out so that it'll be much easier to do algebra with it. All right, let's look at an example here. Let's say, let me get my notes. Let's say that there's an oscillating system that's being damped, as the jargon goes. There's friction taking away mechanical energy and making the amplitude decrease. Specifically, let's say the amplitude gets 2% smaller every 5 seconds. And just to keep this simple, let's say the period of oscillation is half a second, so that in every cycle of oscillation, the amplitude is 2% less than it was at the beginning of that oscillation. So what's the time constant in that case? Well, go back to our basic rule. The amplitude at some time equals original amplitude, e to the minus time over tau. We want to figure out what that number is, so we need to get it out of the exponent, so you can see that we're going to be doing this kind of thing. Well, let's say we just let it go and then just watch for half a second, just watch for 1 cycle. So we're watching for just an amount of time equal to 0.5 seconds. This will be 0.5, and then we know that the amplitude after 0.5 seconds is just 98% of what it was originally. That's what it was originally. So 0.98 times original amplitude, and that's equal to amplitude e to the minus time, which is half a second, over tau. Now, use this now. Use this equation. There's an a on both sides of the equation, so you can just divide the whole equation, get rid of that a, and then what have we got? We have 0.98 equals e to the minus 1/2 over tau. Now, take the natural log of both sides. If you do the same thing to both sides of an equation, both sides are still equal. So the natural log of 0.98, your calculator can tell you what that is just equal to the natural log of e to the minus 0.5 over tau. but the natural log of e to some exponent is just that exponent, because a natural log is an exponent. It's the exponent to which you raise e in order to get whatever is in this slot here. So obviously the power to which you must raise e in order to get this is minus 1/2 over tau. And that minus sign is appropriate. It all works out because your calculator will tell you that the natural log of any number less than 1 is negative. So this will be a negative number, canceling out this negative sign here, so that tau itself will be a positive number, right? A length of time. So you ask your calculator to tell you what the log of 0.98 is, and then you find that tau is actually about 25 seconds. Okay, so here, in this case, we knew how much decay of the amplitude we had in a given amount of time, and from that we were able to figure out the time constant. You can do it the other way around. If you know the time constant, you can figure out how much the amplitude decays. Something like this. Let's say, if that's the time constant, then let's ask, how long does it take to have the amplitude decay all the way down to just 10% of what it was originally? So we're looking for the time it takes to get down to 10%. That is amplitude after you've been watching for t 10% amount of time. The amplitude will just be equal to 10% of the original amplitude, or amplitude over 10. Okay, but this, of course, we know how that works. Amplitude as a function of time is just original amplitude e to the minus time elapsed over tau. Time elapsed in this case is the unknown thing that we're trying to find. And tau we just figured out was 25 seconds. So again, just like before, in this equation you've got an a on both sides of the equation. You can divide the whole equation by a to get rid of those a's, and you're just left with, write it over here, you're just left with 1/10 equals e to the minus time that we're trying to figure out divided by tau, which is 25 seconds. And then do exactly now you're going to do the same thing as before, except you're going to solve for t instead of tau. You already know tau. So natural log of the left-hand side equals natural log of the right-hand side So natural log of e to some power just gives you that power, just pulls that power out of the exponent. So minus the time that we're trying to find divided by 25 seconds. Or to put it another way, 25 seconds times the natural log of 1/10 equals minus 1 times the time that we're trying to figure out. And again, this is a number less than 1, so the natural log for any number less than 1 is negative. And so the left-hand side will be negative. That'll cancel out this negative sign and leave you with a positive amount of time the way you're supposed to. So the time that you come up with then, how long it takes for the amplitude to decay down to 10% of what it was at the start, it comes out to about 58 seconds. Almost a minute. Okay, that's how exponential change works. We'll look at other examples of exponential change at other points here during 2202. But that's the idea. One more thought about exponential change. This is all about how the amplitude changes. If you know how the amplitude changes, you can figure out how the actual mechanical energy changes. But remember, mechanical energy is just proportional to amplitude squared. In other words, however amplitude squared changes, mechanical energy changes exactly the same way. When this variable called amplitude squared changes by some factor, mechanical energy changes by exactly the same factor. So let's look at this example. Let's say you've got an oscillating system and there's a friction force that's damping it, and let's say 60 seconds is the time constant. That is, in 1 minute, the amplitude will decay down to just about 37% of what it was 1 minute earlier. So what happens in 10 seconds? How much does the amplitude decay in 10 seconds? And how much energy is lost in 10 seconds? So first we'll figure out how the amplitude changes, and from that we can use this idea to figure out how much mechanical energy is lost. So same deal, amplitude after 10 seconds is just original amplitude, e to the minus 10 seconds over a time constant of 60 seconds, or e to the minus 1/6. And that will come out to be a times about 84.6%, or 0.846 times A. Right? The amplitude after 10 seconds of damping, 10 seconds of having friction do its work, is just about 84.6% of what it was 10 seconds earlier. So that's how amplitude itself changes. And so you've lost roughly 15% of the original amplitude in those 10 seconds. How much mechanical energy will you have lost? And the answer is not 15%, because it's amplitude squared that keeps track of the mechanical energy, not just plain amplitude. So we want to know how amplitude squared changes. And then when we know that, we'll know how energy changes. So amplitude after 10 seconds is just .846 times the original amplitude. Call it amplitude at 0 seconds when you first turned on the stopwatch and started watching things. Well, we want to know how amplitude squared changes, and you can get that from this equation just by squaring the whole equation. So square of amplitude after 10 seconds is just square of the right-hand side, 0.846 squared times original amplitude 10 seconds earlier squared. So the factor by which a squared changes is 0.846 squared. So that's the factor by which mechanical energy changes. Mechanical energy after 10 seconds is just this squared, and that squared is about 0.72. Or about 72% of however much mechanical energy you had 10 seconds earlier. So the amplitude is decreased by about 15%, or 15.4%, and the energy, mechanical energy, has decreased by 28%.